understood in the last class, the topics that we have covered. Okay. We spoke about linear computation of vectors, linear transformation and matrices, and we understood how signals will be processed and how signals samples and multiple samples are going to be used to find out some outputs, like how we replace one in equation some values. The same way in a wave, there are some other auto-generated or customized generated waves will be added to the waves, and the modification will be done. Alright. So we have given an example of 3x plus 2y, where x and y are waves being replaced with some values, then we'll get one answer. Right? So same way we explained how a continuous signal like audio, when I speak, I record that audio and keep it in a wave form, and if I modify it to like the male voice or maybe the female voice, then I will modify it by adding some more extra thing to that. Okay, that we told by saying we can we said the samples are then mapped with the Fourier transform into a sequence. Samples will match it. Alright, and we also said that whenever we wanted to find out different parameters in the waves, signals, we can capture with that method. We can capture with the method of Fourier transform. We can find out the amplitude in the frequency domain and the phase. That is, we can also find it. And we also mentioned how a cos signal that is getting started initially at a 90 degree. Okay. So that we have did it. We just simulated in Python program with the help of NumPy, SciPy, and Matplotlib. NumPy is used to access the generating numbers. Like earlier we had a range function which was generating multiple numbers. Now we have a range. Okay, that is going to have same functionality as the range earlier. And then we learned about how cos is actually giving us these points, and we also tried modifying these values like 2 and 4, and we saw that the number of points are actually missing when we add.
So what the time is what is the snapshot will be like 4 lines?
This one?
Yes.
That means this will generate the plot in the same line. Inline is expand the definition of Matplotlib in there itself.
So the red line will be the default access.
Default access. Default means you have to see plot. Yes. Okay. If you want to know more about STEM, you can go ahead with that, because we are not considered this thing in when we are learning about the plots. Okay. We just learned few of them. Nice, connecting that thing. Sanjay? Sanjay, am I audible?
Audible, sir.
All right. Okay. So this way also you can make only positive points are there. Starting from 0, and there are no minus points or negative points on 0. So these points here. And what they have used sine angle, and they have used 2 into pi comma 41 the line spaces. And you can also change the shapes of this one. That is a marker D. D is a diamond. That way you can use this pen. Okay, what we say? Visualization library in 2D. Plot Matplotlib is multi. You understand that? Creates a stem plot. As stem plot plots vertical lines at each x position covered under the graph from the baseline, that is the red line that you saw earlier, to a y. Okay, to a y. It is touching on the left side. And this is a marker there. And these are the parameters that we have: x, y, line FMT, then marker FMT, and then base FMT. Okay, all the parameters are here. They're optional, that's why they're not given. Default plot, stem plots vertical lines from baseline to the y coordinate and place the marker at the peak. These are the markers at the peak. By default, they are circles. Okay. So we also discussed how an input vector could change linearly to the output vector. And we also understood how the transformation happens conceptually, and we did a small program on that how a vector in 3D space could be represented with the help of two values, x and y. Okay. When we wanted to go with a 3 dimension, we need to switch to other libraries which have the plot to be visible in terms of 3D plots. Alright? Presently we are not doing that. We are just sticking to the vectors having one line available in two coordinates, x and y. Okay, we did this and we found that values, this is my minus values. Same way, this is 0, plus values, minus values. So this is my y-axis, plus y-axis. This is my minus y-axis, plus x-axis. Okay, that way, this plus y-axis, some value is available at this place, and this is my minus x-axis. From this point, something is available, some value is available. So what is my value presently? X value is minus 3. For example, this is minus 2. Minus 3 is somewhere here. Right? So exactly if I draw like this, so this is my minus 3. So another number is minus only 2. That is my y, which is positive y. So this is my positive y. In that, this is my 0 and this is 2. Exactly from here, this is 2. So this is what the point it is pointing to from the origin. Alright? That's how a vector could be drawn with the from the origin to the vector. Two parameters are basically available for Q vector. Alright, and this is the color and the scale and units. That's x and y axis, 2 units. Alright. Then we need to go with how do we manipulate and how do they change their values. Moreover, this the same transformation can be applied not only to the single vector, but can be actually applied on a whole set of vectors. So basically, if you want to transform the whole plane in a different, what you can say, plus y, 2x plus 3y will be one of the functions. Alright? So if I consider that, I can replace my values which are independently available, x, y values. So when I replace them, I'll be getting some value, the other values in that specific places. Okay? Then those values, if I consider them as one of the new vector, then my new vector will be anywhere in the plane, but they will be available on the available with the same vector magnitude, but the coordinates have got changed. Right? Okay. So that's what we are saying here. One way to visualize this is from A to it has went not considered as a study. So you consider them as okay. The point minus 3 comma 2 moved to 2 comma 3. That is the change that has happened after transformation. So that's what is one. So if I have minus 3x plus 2y, I can transform it to 2 comma 3 or x comma
3 is changing its place also and the sign also.
exactly.
Whereas 2 is only changing its positions. By multiplying or doing by Watson, 3 is changing its position in two ways.
You can see some examples over it.
It's changing position and direction.
Right. So we'll see some examples and go ahead with that. I'm not added some examples already. Let's have some examples. Vector space linear transformation. Okay. Linear transformation itself will take it as a beginning. We'll go to GFG. If we study this vector space, I understand what is this. You understand what these are. A group of objects called vectors additively and multiplied, scaled by the number and called scalars, values together. I hope we discussed it and we also given some examples. Without this thing, you vectors. We have two vectors. We have two individual vectors A and B, and we make A plus B. It says corresponding components will be added. X-axis to Y
and Z to Z.
Okay. Got it? X to X, Y to Y. Else it is no meaning if you add everything. So A will be added to A1 will be added to B1, 2, 2, 3, 3. That's it. Equal. Vector and scalar is just an integer. A vector and a scalar, which is just an integer as a magnitude, are multiplied in scalar multiplication. If you multiply a vector V by a scalar C, we get a new vector called C into P, whose magnitude is C times magnitude of V. magnitude is, the total magnitude is C times, that is scalar times the magnitude of vector, because you are multiplying obviously, like 2 into 3 or like a thing. Okay. If you want to subtract two vectors by a linear algebra, we can do like this. How do you do that? 4, 5, 1, 6, 1, 7. So this is U and this is V. This is the vector symbol on top. Okay, the arrow is vector symbol. When we subtract 4 minus 6, so this is my new vector. This is my new vector, which will be the resultant vector after subtracting two vectors. Okay, this is my transformed value. This is my two vectors. That's it. Yeah, product value calculating unit vector. Okay, linear functions we have. Understood linear functions? Or if you are not answering equally with the linear transformation, straight line. Okay, so x and y will gradually change the values equally. Okay. You see that we are having a complete one cube connecting all the coordinates. Then that will be one of the vector space. So we are saying vectors as it translates vector space to other vector space. Okay. Do you understand this? I mean this one. F of x is a scalar. F of x and f of y are vectors. Okay. In the range of f and x and y are vectors in the form of in the domain of f. The domain is the space that you have. Do you understand this one as well? F of ax is the function that is going to be affected. Okay, and this is going to be operative. If this operates, then these things get affected. If these operates, then this gets affected. That's what we are trying to say here. F of x and f of y are vectors which are having operations among them. So here we are multiplying a scalar and a vector. Scalar and a vector we are multiplying. That's what is happening. Okay. I hope all of you.
Y equal to 0.
Okay.
Simultaneous linear equations means they will get a degree simultaneous. So x square plus x equal to 0. That's a simultaneous. So solving linear equations is you need to subtract one from the other by equating one of the variable. Graphing linear equations.
No, that is not the one. But these many I wanted all of you next time when you come to the class, I want all of you to read them and come. I will explain that. I want you to explain.
So what I said,
No, that's right. Okay. You mentioned something in vectors. Let's consider an example of vector. To understand, suppose we have two vector v1, v2 in dimension in a two-dimensional space, that is x and y. We have only two values. v1 equal to 1 and 2. That is, we'll apply linear transformation that doubles the value of the first component and subtract the value of the second component. Is that right? We can represent the transformation as two linear matrix. Is it right? So what it says, the linear transformation that doubles the value of the first component and then subtract the value of the second component, and we can form the 2 cross 2 matrix. Let me know how it happens. Just a second. Do you understand all of the matrix? Very clear. Okay. Okay. No problem. Here we can simply multiply the matrix with the vector 1. To apply this to vector v1, simply multiply the matrix A with the vector 1, and you'll get this 2 minus 1, 0 minus 1 multiplied with 1 and 2, you'll get 0 and minus 2 as a v1 vector, and the resulting vector will be 0 comma minus 2. Is the transformed version of v1. Because you're going to, at the end, you have the component of scalar in the vector. So that magnitude will be multiplied. That's what it is. It is holding the component. That component you are utilizing for multiplication.
So if you multiply a matrix currently within a matrix, you multiply it by 1. So 1 will be multiplied. Scalar multiplication. When this will become a vector multiplication?
It is vector multiplication only, but when you multiply, you are using magnitude and sign. Obviously. When we say vector multiplication, we mean that we are multiplying two vectors. But in calculation, we definitely use the magnitudes. Okay, let's see one second. B is my one of the vector having 4 comma 1, 4 and 1, and I'll do 5 to B. This is my vector, and this is the quantity that I'm going to multiply. I multiply with this 5 to these things. They are the numbers that I'm multiplying. Example. We have taken a matrix of the 0, 0 array. We have kept 4 comma 1, that is other values. Okay, one vector of the range. Let's take one more example. Multiplication of secret.
Yes.
Dot product multiplication. Result is a scalar quantity. If A equal to AX, AY, AZ, B equal to BX, BY, BZ, A dot B will be this one, and at the end we get a scalar quantity. Cross product. This is resulting in a matrix. One array taken, this one matrix, this second matrix, and you're going to make a cross multiplication with them, or cross product of two vectors. This is one vector and this is another vector, and these vectors could result in another vector itself. But there is multiplication only. Overall, but magnitude wise, it will be multiplied. Very good. Okay. The resulting vector 0, minus 2 is the transformed version of V1. Similarly, we can apply the same transformation to V2. We are getting 3, minus 4 transformed to V2. So, what was the V1 and V2? Initially, they are 1 and 2, 3 and 4. Now they have changed to 0, minus 2 and 3, minus 4. Alright. If you draw it on a plot, then you see the transformation that has happened onto the plot. Okay. 1, 2. Where do they come in terms of the positive first quadrant? First quadrant, X value is. Okay, let's draw these lines. Yes.
Can I have some graph on the screen?
Graph on screen.
Yes. Google Pro images graph, you may get some graphs on the screen.
For editing.
To demonstrate these examples.
Okay, examples. Okay. See, the planes that they are changing are actually in 3D space. So the plane was like this, and they just modifying it. The shapes of those plane blocks are not changing. Don't think in that angle. They have become the diamond shape. They are not diamond shape, but we are looking in that angle. That's why they are looking like a diamond shape. This is one plane. The background is one plane. This is another plane. They just wanted you to show. I mean, see how they are being modified. This is 90 degree, and away from that, it is having angle. There are two vectors. They're just showing. That's it. Nothing more. Understand the values here. 3, 2, 3, 1, 1, 2. 1 and 2 have been taken, and 3 and 1 is already here. Another vector that is -1 and 2 has been taken, and that will be mapped. 1 and 2, 3 and 1. This -1, this is 2, and this will be added. This is pretty clear. L of I changed to used to be right of L of I. This is your x and y, and this is another plane that is available on either side. We have so many visuals actually. If you can understand, that's the goal. In this space, you can understand actually. We're drawing the z-axis in India. Let's look at three vectors in 3D space. As I told you, imagine the room. So there are 3 axes available. So you just see 2 vectors and they take it. And another vector is already there in a yellow space. And this is got transformed from this place to this place. Visually, if you want to see from above, yes, I hope all of you understood. In multiple vectors, eigenvalues are also one of them. Multiple vectors in one plane, and we're just trying to expand with one of the multiply. Nothing more than that. The space is just getting expanded on a one single plane. Okay. Let's see one example.
It's like stretching the films. Photo.
Yes. the vectors at the points will also be moving away and they will be distancing from each other. Let's look at it how it is happening. 2 cross 2 matrix as a linear transformation. A, B, C, D, and X and Y as vector. And we have another matrix which we are going to make a dot product. And this is how we multiply. Is that right? Okay. We're just saying that whole linear transformation is defined with the two transform basis vector. We can then map the plane if we know the transformation base vector. Okay. Transformation base vector is the initial vector that we are going to consider to multiply an existing vector. Each of these vectors is specific with just two numbers. In this case, we have using two vectors, we can put them here we see why that length is larger and why those coordinates have got changed at the end. We are saying clearly here, using these two vectors, we can put them into 2 cross 2 matrix, two vectors into one matrix, and we are considering them to be available in the same plane. Okay. In such a way that we stack these vectors along with this 2 cross 2 matrix present using the matrix that we can use it to further processing as a matrix multiplication. How we multiply A with X. To simplify, we have just taken X multiplied with A and C. Is that right? Yes. Plus Y multiplied with B and B. And then we have A into X, X into A, Ax plus By, or Y into B, and then Cx plus Dy. So with this, you'll get one whole value at this place. Now, your three values, one vector, two vector, and another coordinate, are becoming one value, which is my resultant vector, which is my transformed vector. All the same in the earlier example, animation, we are just scaling the existing vector to the scale that we have used in the matrix. Okay, I should zoom. We have 1, 1, 2, and minus 1 and 2, and draw it here. So, what are the values I should draw and where I should point them? 1 and 2 as the second vector, and are both of them are in the same plane. Understand that animation clearly.
So there are only two planes.
Two ways.
We are getting used in that it is a 3D.
It is trying to show in 3D space that we are connected.
I don't know, there are only X and Y.
X and Y axis. Presently, the last photo that you see, I'll just make a full screen in that case. the pictures that will be available. Screenshot. Four options. Plus x plus y plus x minus plus x plus y minus y plus x coordinate, second coordinate, I mean fourth coordinate. Second coordinate plus y minus x minus y. Only four options we have in two dimension. So just to explain you, they have just modified the diagram. Okay. In other thing, if you want to look, they are actually same. Okay. That is 45 degree.
Sir, this green line, sir. That is three times the length of the red line, sir.
Right.
See, now it's visible.
After multiplication, it is giving that value. Okay, no problem. You get the same according to this one. Okay, so what will be the resulting value? We'll have 79, 39 as one of the value. You want me to put that on x-axis? They have like this. You are saying here only they have 1, 3.
Yes.
And you are saying somewhere here they have that one more 2 and 4. 2 and 4. Okay. Somewhere here 2 and 4. Right? Obviously, you consider the same way. Like this is here and this is here, and you take the graph, you get the same place. That's what here they did in the transformation they wanted to show. Else they would have done the transformation according to that diagram here itself. First time when they are rotating, you are getting no, but second time when they are merging it, they are taking it in 45 degree. Okay, no problem. I'll leave that thing. 2413. Okay. How about this one? We have this 5 and 6. This is 5. 1, 2, 3, 4. This is 4. This is 5. I need that 5. Then I need 6. 1, 2, 3, 4, 5. This I consider 6. So this is where my point is. So after adding all of the points, that is my 5, 6. So all those vectors, they are visually showing. We just calculated and trying to put those values. Now the resulting value that we have is 17. Last transformation, 17 and 39. So we will have it somewhere. Somewhere out of this scale. 17 on the x-axis and 39 somewhere, and all of them have scaled to the next level, and that's what the point is being shown. That is your 79, 39. In terms of any number that you're considering, I mean the second point that you consider 5 and 6 is the important quantity that you are using. So all the quantities which are available as 2 vectors. Okay. All right. Onto this slide. Okay, just a second.
All these things, matrices and tensors, they are in use.
Whenever they have been discovered by mathematicians, I don't know.
In terms of this, in terms of computers,
Computers, okay. In the computing power,
when they time, it was a theory, sir. When they were applied into computers.
I need to check. See, whenever we started programming, we already have the control over the text as well as the numbers, and the manipulation or the mathematical computation is obviously happening. And to process vector or complex values, you need to have more computing power. So definitely you would have crossed the third generation.
Probably some 20 years back, they recently started.
Yes. Might be before that also, not in our country, but in other countries where most of the mathematicians originated. They are more curious and they are more ahead of what we have. Mostly in terms of innovation index, we are at 36. Innovation index list, we will not count. So all those countries can be mapped as one of the early adopters of such technologies. Netherlands, USA, all these, most of them are there. I will send you the list also. So those are the people who have gone through it. Okay, I'm talking about tensors. Yes. Okay, let's talk about tensors for 2 minutes. We initially spoke about scalars, and we said that it only has a quantity, like temperature. If I have coffee, if I want to check what is that, it's just a temperature. It gives just a value. When I want to say I have went from A to B, then there is a question. Okay, I understand you went in this direction, but at what speed or at what distance you covered? That number will be a scalar value. Direction will be one more quantity in the measurement. Okay. So with that, we understood three-dimensional value as a. All right. You can also write it like in the terms coordinate x, y, z. That's one point in the 3D. It's like I just mentioned in the rule. Column vector. This is how you represent.
There's a matrix of order 1 into 3, and the pink one is 3 comma 1.
3 goes to 1 column.
And what do you call that third sky blue color one's a matrix?
2 comma 3.
Or a storage space for row or column vectors? 1D vectors?
1D vector will not be there. That's why we are calling them a scalar. If it has one value, for example, if I put the rank in tensor, I just saw the 3D box. During the rank defines how many 2 dimension, 3 dimension, what kind of a dimension the rank will tell. Shape which defines the size of each dimension of the data. Data type which it does not explain the tensor. It is explain the library available to use to implement the TensorFlow. Let's take the article which explains us the TensorFlow. Okay, we have seen this word earlier also. I explained this one, saying that TensorFlow is one of the startup which has been acquired by. No, okay, this is the development of the Google, which has developed this library and created like a website where you can go and deploy your models and try to use the TensorFlow capabilities for your machine learning models. If you have created a small model, you can upload there and you can check your models. And you already have ready models to check. So that platform name is a TensorFlow. Alright? And it's called a framework, you can call it. A framework to define and run computations. Whenever you do computations in machine or in TensorFlow, the basic units of computation will be tensors. Alright? find ML solutions level and go from research level to production level. Research level is just concept level. Production level is the ready to sell. The ML on the web, on the mobile phone, on the server. And if you are doing something on the, if you want to do something on the web, you can use the tensor. Capability in terms of storage and processing, they can have this thing. And servers also can have that. Okay, that's about tensor and TensorFlow and what tensor is, I mean, why tensor is important. I hope you understand that. All right. Okay. The matrix, the potential. Got it? Okay. I want all of you to explore and create an account in TensorFlow. Okay, and get me the list of models which they are kept it ready. Okay. Next topic, that is linear algebra in neural networks. So this whole module, I mean this topic, will speak about the mathematics used in the neural network. Okay. So first we need to understand what technology, in what technology the mathematics is being used. Then we see what mathematics is being used. Two questions we need to solve here. Okay, let's understand what is the neural network. First, this one. Let's break down this word into neural and network. What does that mean by neuron? What does that mean of neuron? Huh? Nerve cells, exactly. Nerve is the complete nerve. Okay. Where it exists in human brain, it exists. We call it as one cell as neuron. All right. How do they communicate? Dendrites. Okay, let's check. Okay, but they have some connectivities through which they'll be able to connect with other cells and they'll be able to communicate. Okay, and they are how they are going to process and combine how they are going to process and how they are going to use it. whether it is I have 1%. I have 99% guarantee that this is the one. 1% I have to mention. So only two people I want, two nodes I want. Then I try to have the confirmation. Alright, that is how people involved in making decisions. Here nodes we call them, which get involved in computation. Okay. Here we mentioned here a neural network is a powerful mathematical model. Mathematical model. It will be a combination of multiple formulas combined together meaningfully. Okay. And relationship between all the formulas have been established to accomplish our task. Okay. I wanted to manipulate my color video to black and white video. That's my task. I will adjust those formulas accordingly, mathematical formulas accordingly, and create an algorithm. And that algorithm, what it does, give input a video, color video, output black and white video. Get it? So what is your mathematical model here? We have a set of formulas being added, and those connected formulas are going to give you output. What those formulas are there, we'll see that. But just try to understand the blueprint of how it is happening. Combining the linear algebra, mathematical model combining the linear algebra, biology. So I hope all the three you have learned. Biology you have not done. To solve different problems, we have different. We need to design a models with a unique algorithms. The network takes of neurons, amount of inputs. Okay, so if it is 6, 7 are there inputs. 6 input, 6 programs are there. 6 programs will receive 6 inputs. Okay, that's the inputs needed to design. The network takes the given inputs and then calculates the targeting the actual result. Okay. So whenever you train your model without untrained models, will not give you the actual result at the beginning. And once they understand what your modifying the values or the inputs, then you understand what has to be modified. Okay. We will also see them in animation, and there is a specific website where you go, and I will allow you to use those in your laptop to modify those parameters and just see how dynamically you can change the flow. All right.